Yeah, so the last speaker is Yang-Hui from City University of London, Oxford, and Nankai. He will talk on the Calabi-Yau volumes and the reflexive polytopes.
Well, thank you very much for having me here, and thanks especially to David for inviting me. My talk is, my talk doesn't have any higher, twisted, or almost, but it does have Calabi-Yau. And this is based on work with Rak-Kyeong and Professor Yao, which should appear next week. So let me just begin with some very, very rudimentary definitions from childhood. So we all recall that a convex lattice polytope, all of my polytopes will be lattice polytopes. There are two equivalent definitions. The first of which is it's called the vertex representation, and the second one is the so-called half-plane representation. The vertex representation takes a convex hull of a set of lattice points, which I'm going to call some points P, right? And it's just this particular, the convex set. And equivalently, you can define this as the intersection of integer inequalities of such a type. So you're just slicing things by hyperplanes. Okay, and then the extremal points of these things I'm going to call vertices. So that's dimension 1. Dimension 0, dimension 1 things are edges, and 2 faces, 3 faces, all the way up to n-1 faces, which are called facets. And dimension n objects will be the convex lattice polytope itself. So of course, we're familiar with the n equal to 2 case. I'm going to use the subscript n to denote the dimension which this convex polytope lives in. So dimension 2 will be polygons, and dimension 3 will be polyhedra. Okay, so this is very standard definition. Maybe slightly less familiar is the so-called polar dual of the convex polytope. And this is just a set of points which, in R, which obey this inequality. So you're just doing some kind of a duality condition for these. Now, if you did this in general, this polar dual is not guaranteed to be an integer lattice polytope. Because if you just solve these inequalities, the vertices of this thing will in general be rational points rather than the integer. But in the case that the vertices are indeed integer, and that this dual, this polar dual, is indeed a convex lattice polytope, I'm going to call these things a reflexive lattice polytope, or reflexive delta. And of course, this definition, you can easily check that it has a duality condition in the sense that two circles cancel each other. If further, indeed, that a lattice is equal to its polar dual, these things I'm going to call self-reflexive or self-dual. So just to give an example, this is an example of a delta 2 in this triangle. The vertices are these, or you can represent these by hyperplanes or lines in this case, and its polar dual is this one. And you can check, indeed, the vertices are still integer, so this is very good. And equivalently, these are sliced also by hyperplanes. So this is indeed, these two will both be called reflexive polytopes. This is not a self-reflexive polytope because this is not the same as this. So you can easily check, there's a theorem, that the reflexive simply means there's a single interior lattice point, which you can set to be the origin, from which all of the other hyperplanes are distance 1 away. Now this seems like a very, it's a standard but a fairly esoteric thing in combinatorics. But what is powerful is that from this polytope you can construct from a standard way a toric variety of complex dimension n. So the way you do it is you take the face fan of the polytope, or any one of these, which is simply this positive span of the generated. So for example, if you take this delta 2 example that I had earlier, the face fan will just simply be this one, and this one, because it's the positive generation of these. Then that's great. So this face fan then defines in a standard way a compact toric variety of complex dimension n. So this is a very nice, I give you this is true of course for any lattice polytope, but in particular it is true for reflexive lattice polytopes. So in the case that we're interested in, when this delta is reflexive, such a toric variety will be called Gorenstein Fano toric varieties. So in the sense that its anti-canonical divisor is Cartier ample. So you can sort of think of these as, so Fano is just simply the case that these things admit positive curvature. And Gorenstein Fano is that they allow mild singularities which can be resolved. So, of course, there's another standard theorem, is that a toric variety is smooth, of course, if all of the cones are smooth, in the sense that all of these generators form a part of a z-basis. In other words, all you need to check is that the determinant of various these determinant formed by columns of these vectors is plus minus 1. But of course, this is not true in general for polytopes, and it is not true in general for reflexive polytopes. But when these things are smooth, in the reflexive case, there will just simply be toric Fano varieties. Okay, so why is this interesting for physics? This is a beautiful theorem of Batyarev and Borisov that go back to the 90s. They simply said, had this very nice construction that if you take the anti-canonical divisor in this Gorenstein Fano toric variety, take a hypersurface defined by the anti-canonical divisor, and if you take this to be generic enough to miss all of the singularities, it'll give you a smooth Calabi-Yau manifold of complex dimension n-1. Okay, so this is sort of the hypersurface construction of Calabi-Yau varieties. And then Kreutzer, physicists Kreutzer and Schacke took this theorem and went hardcore on this. So they said, well, if I took a reflexive polytope of dimension 4, of real dimension 4, this will construct for me a complex Fano variety of complex dimension 4, and I take the hypersurface defined by the anti-canonical divisor, this will give me smooth Calabi-Yau threefolds. I will explain in a minute why Calabi-Yau threefolds are interesting for physicists. Well, actually, let me just explain that now. Because string theory is a theory in 10 dimensions, and the most important equation in string theory is that 10 is equal to 4 plus 6. 4 is our space-time, and 6 is the remaining compactification, or the extra dimensions, and then the second most important equation in string theory is that 6 is 2 times 3, because you complexify the remaining 6 real dimensions into some 3 complex variety, dimension 3 complex variety. And in particular, Calabi-Yau will guarantee you nice behavior of the transverse, this 4 dimensions. I don't have to define Calabi-Yau so much because Katrin did a wonderful job this morning, so that spares me some time getting into the details of Calabi-Yaus. But the point of this construction is that for every one of these reflexive 4 polytopes, I can take this hypersurface and I can create this. And what is remarkable is that they use 1990s technology on the computer. This is, even today, this is not trivial, right? And they found something on the order of 10 to the 10 Calabi-Yaus. Okay, because you can classify it for every one of these, you can get some hypersurface, you just put it in a computer. The data itself is over 50 gigabytes. It's quite nice, actually. I have it there somewhere if you want it. And what's interesting is that then you get 10 to the 5th distinct Hodge pairs. So this is now this sort of become an iconic picture in string theory and perhaps modern physics. If you just plot the sum of Hodge numbers versus the difference, the sum of the Hodge numbers versus the difference of Hodge numbers, which is the Euler character, you just get this plot. This is, of course, the best experimental evidence for mirror symmetry. The fact that this looks explicitly left mirror symmetric shows that this is true. And so this is Philip Candelas' favorite picture. In fact, you can see this in his office. It doesn't have my contribution to this picture is to put the colors. So the colors is a log density plot of these 10 to the 5th, so of the 10 to the 10 number of multiplicities. So, right, you got 10 to the 10 of these data points, but 10 to the 5th are distinct. So you can see the most dominant, the most likely Calabi-Yau threefold that we know of is the 2727 self-mirror manifold that lives around over here. There's about 1 million of these, which is an order magnitude more than anything else. So there's some other fine structures. You can go on and on about doing this. But what is beautiful about Batyarev and Borisov's theorem is that mirror symmetry is a combinatorial fact that if you construct a Calabi-Yau hypersurface in delta, its mirror will be the one in the polar dual. So polar duality in reflexive polytopes corresponds to mirror symmetry in Calabi-Yau. Okay. I'm very excited about the plot because this has nothing to do with my talk, but I love it so much, and physicists love it so much. If you ever talk about Calabi-Yaus and reflexive polytopes, this diagram should be shown. Anyway, we will not do this. We'll do something quite different. So before I tell you what we're about to do, let me just give you some very concrete examples, right? So I said these polytopes are in dimension whatever, and in dimension 2, there will just be polygons. So let's look at these called polygons. And it's a classical theorem. Actually, I don't know to whom to attribute this because it's so classical, that all reflexive polytopes in dimension 2 are GL to Z equivalent to one of these 16. Okay, you can probably just check it. So these are the ones, all of the convex lattice polygons with a single interior point, which is this green, which is the origin, and all of the other hyperplanes or lines are distance 1 away. Okay, so in particular, you can see that. So this is drawn in a nice way because top and bottom are polar dual. Everything in the center is self-dual. Right? And the vertices go from 3 to 6 maximally, and the number of total lattice points go from 4 to 10. So this is just, it's a fact. And these 4 are self-dual or self-reflexive polygons. And in particular, you'll see familiar to any toric geometer is that you'll see the 5 smooth ones. So these are the 5 smooth Fano surfaces or Del-Pezzo surfaces. In particular, they are Del-Pezzo 0, 1, 2, 3. I'm using physicist notation. By Del-Pezzo 0, 1, 2, 3, I mean the Del-Pezzo surfaces of degrees 8, 7, 6, 5. This is just because I'm using this is P2 blown up at this number of generic points. So 9, 8, that's what I meant, yes. 9 minus whatever this number. So this is Del-Pezzo 0, Del-Pezzo 1. I think this is first Hertzebruch surface P1 cross P1. So you'll see the 5 of these are very special because they're in fact smooth. You can check that the determinant of the adjacent vectors formed are indeed determined plus minus 1. So that's great. So if I took the Borisov-Batyrev and Kreutzer-Shkake construction, I would have taken a hypersurface in one of these things, but that would just give me elliptic curves. Okay, so that's not what I'm going to do because this is dimension 2. I don't want to go 1 dimension down. I want to go 1 dimension up. Okay, so if I did go 1 dimension up, what would that give me? Is that there will be on top of these things, I'm going to have some kind of affine Calabi-Yau threefold. Right, so that's the moral of the story. So to one of these, I'm not going to consider the 16 elliptic curves that come from as hypersurfaces. I'm going to think about the Calabi-Yau 3 cones over these. So if I just sort of affinize, so these are projective varieties, I think about the affine cone over these. Because these are Fano, the affine cone is actually Calabi-Yau. And in fact, in this case, Calabi-Yau threefold. Okay, I'm going to talk about that I'll go back to this point in a minute. Now, let's just go back to this classification problem, which is a really hard one. Okay, so it is indeed true that the number of GLN-Z equivalence classes of these are finite in every dimension. This is shown. So then the list goes up a bit. So in dimension 2, there are the 16 that I showed you, of which there are the 5 Del-Pezzo surfaces. In dimension 3 and 4, this work by Kreutzer and Shkake. Kreutzer sadly passed away in doing the next dimension. So dimension 3, there are 4,300 of these, and in dimension 4, there are 473 million of these. And the regular ones, the smooth ones, are actually very rare in this. If you just focus on the regular ones, the works of Kreutzer, Nil, and Obel, and Pfaffenholz have actually increased it up to dimension 7 or 8. So it is not known what the generating function for this is, either this sequence or this sequence. It is in OEIS. Nobody has any idea what these are. There are some estimates on the growth rate of these, but you can clearly see that it's an exponential growth rate. But this is great because there are a lot of these, and physicists like data. So for us, this is data, right? Well, let's just play with it. This is awesome. Let's just play. And it's even better because this one and this one have been very kindly built by Fokker-Braun into Sage. So this is not only data, but available and computable data. So for the dimension 4 case, there are various collaborations. There's one group in Vienna following Kreuz and Schkake, and there are 2 collaborations that I'm involved in, one with Oxford London, and the other one is sort of a big collaboration just to sort of data mine this set. So now let's go back to the kind of toric Calabi-Yaus that I'm actually interested in. So I'm going to consider, as I said, I'm going to consider the complex cone over this Fano compact, not necessarily smooth, base. Okay, so now I have to think about for every one of dimension n-1 reflexive lattice polytope, I can create some kind of singular affine variety, which is Calabi-Yau. The Gorenstein property of these Fano varieties guarantee that this is actually Calabi-Yau. So then I'm just going to simply call these things a toric diagram, right? So I can just take one of these, and I will say for every one of these things, this is the associated toric diagram of this Calabi-Yau. Of course, no compact Calabi-Yau is toric. I have to emphasize these are affine and possibly and generically singular Calabi-Yau varieties. So, and of course, you can do this in general, but we're going to focus on when this is reflexive, just because we have the largest database of these. Right, so, in fact, you can take any lattice polygon, convex lattice polygon, and do a construction, and you can have a Calabi-Yau threefold, which is affine and singular. So let's go back to this example. So we recognize this one as P2, but we're really going to think about this as the cone over P2, and as specifically the total space of the anti-canonical bundle over P2. Right, so that's you can think of this one as C3 over Z3. Okay. Now, these Calabi-Yau manifolds are very, very interesting. So these, I should say, Calabi-Yau varieties are very interesting. Things like these. Right. So, in particular, so if I say, so what is the simplest affine Calabi-Yau threefold? I would say it's just C3. Right? It's not just Ricci flat; it's completely flat, but it's fine. But what's interesting is that C3 itself can be thought of as a real cone over S5. Okay, that's a very important thing. So, and S5 is Sasaki-Einstein. So, in other words, if I have one of these suckers, itself is a real cone. So I've constructed these as complex cones of a Fano variety, but then I'm going to think about this as a real cone over a compact smooth Sasaki-Einstein manifold of real dimension 2n-1. So what do I mean by that is that I simply write down this conical metric, where this metric is the Calabi-Yau metric. Note that I can actually do this because this is affine, so I can actually write down these explicit metrics. If these were compact, I won't be able to write. No Ricci flat compact Kähler metrics are known on compact Calabi-Yaus. But because these are affine, I can actually get away with this. So this is the Calabi-Yau metric, and then it's a conical metric over the Sasaki-Einstein base. So you can set R equal to 0 is the tip of the cone where it is singular, and R equal to 1 is where the Sasaki-Einstein base is. So now it's great. So now I can actually play around with metrical geometry. So in particular, there's a Reeb vector, which is a Killian vector field generated by this, right? Where I is the complex structure on the Calabi-Yau. Now, in particular, if in our case, because they're toric varieties, and that's really nice because they're toric, they come for free with C-star actions. In particular, this is a toric variety of complex dimension n, so there's a Tn torus action on it. So there you can write these generators of this action as d by some coordinates, d by d phi I. And then in fact, and in particular, these will leave the Kähler form invariant. Okay. So now having chosen this, I can rewrite all of these, the entire setup in symplectic coordinates. So I'd say I'm going to choose symplectic coordinates y and phi I, where I goes from 1 to n. And then my Kähler form is just of this. And I can rewrite the metric in this very nice way, where it sort of factorizes between the y bits and the phi bits. And G is some symplectic potential. It's a derivative of symplectic potential, and these are inverse matrices of each other. In these coordinates, the Reed vector take the form of these, if we just write it down. And the components of this, I'm going to call the actual Reed vector. This is very explicit. But because of the Calabi-Yau condition, have 1 degree of freedom to, so essentially, you can say that because there's a hyperplane condition, so you can put one more linear condition on it. You can put the condition that all the b's sum up to 0, or traditionally what is done is to set the last component to n, and that's the convention that we're going to follow. So just few remarks. You can the Calabi-Yau variety is actually, you can think of as a torus vibration precisely over the polyhedral cone, the lattice polyhedral cone that lattice polyhedral polytope that I talked about. And then you can think about the cone is being generated by this setup. So here is, so why are we doing this? Why do I care about affine Calabi-Yaus, right? Because I talked about string theorists are interested in compact Calabi-Yaus. So why affine Calabi-Yaus? So here's ADS-CFT in a nutshell for algebraic geometers. So this is a string theory setup. So this is this ties well with what Yang-Hui said yesterday about what's called a brain configuration. So there are 2 ways to solve this most important equation. 10 is equal to 4 plus 3 times 2. One of which is to take these to be very, very small. And that's the case of compactification. We have compact Calabi-Yau threefolds. The other solution is to take this very, very large. And just imagine that you live in a 4-dimensional slice that's floating around in 10 dimensions. So that's what's called a brain setup. So we live on this 4-dimensional slice called a brain. In particular, in type 2b string theory, this is called a D3 brain. And the transverse directions are 3 times 2 complex. So it's 3 complex dimensional affine directions. So they're non-compact directions. So and they're conical. So in other words, here's where we live. This is the world of gauge theory and whatnot. And the transverse perpendicular directions is some Calabi-Yau threefold. So here, traditionally we think about D3 brains because D3 brains have world volume 3 plus 1, which is of 4 dimensions, which is where we live in. And the transverse direction will be 3 times 2. But you can generalize this. A Dn brain will be of dimension n plus 1 in space-time dimension, and the transverse dimension will be 10 minus n minus 1. And this so this is the most traditional setup where we have this cone over as a real cone over Sasaki-Einstein 5 manifold. Okay, and in particular, this factorization, after you've done this thing, so this is 4 plus 3 times 2. You can also think of this as 4 plus 1 plus 3 times 2 minus 1. And that's ADS5 cross Y. So for example, the simplest example I talked about was when this transverse direction is just C3, right? It's complexification of R6, and your brain is just floating around. And C3 is the real cone over S5. So that's this example. Of course, there are many, many more Sasaki-Einstein 5 manifolds than just S5, but in general, all of these are known as part of this ADS5 CFT4 paradigm. So that's the physics setup, but as far as the geometry is concerned, for our toric setup, it goes as follows. You can take an n-1 dimensional lattice reflexive polytope. You can construct a Gorenstein Fano variety of compact, but not smooth necessarily, of dimension n-1. You consider the affine singular Calabi-Yau cone over this of dimension n, so that's here. And then you take the real base of this cone as a Sasaki-Einstein 2n-1 manifold, and the Reed vector for this can be written, for this Sasaki-Einstein manifold can be written in this way, with 1 degree of freedom to allow us to set one of the coordinates by convention to n. So this one is called ADS5 CFT4 correspondence because the CFT4 is the 4-dimensional quantum field theory living on the D3 brain. But there are other ones such as ADS7 cross, I'm going to mess up my arithmetic, 7, 3, so that's CFT 3, and so on and so forth. Right? So that's the basic setup. So this is not the setup of traditional compactification in string theory. This is what we call the holographic correspondence. There's a holographic correspondence between the transverse directions, where gravity lives, and the gauge theory that lives on the d-branes. Okay. So now, given this physics setup, so of course this is the first realization of this was due to Juan Matecena, and then it's since grown into its own industry in theoretical physics. But now we got the best scenario possible. We got what physicists tell us to do, and we've got a hell lot of data, so we can play with it. So over the years for this setup, sorry, let me just go back to for this setup in dimension n equal to 3, Calabi-Yau threefolds, for toric varieties, this is now well established by many collaborations in P for physics and M for mathematicians, including Alistair and various students of his. So I think because people from M have worked on it, I can phrase this as a theorem. For Calabi-Yau threefold, it says that the coherent component of the Nakajima quiver variety, the representation variety of a quiver, whose representation variety is this Calabi-Yau threefold, toric Calabi-Yau threefold, when the quiver and the simple potential is graphed due to a bipartite graph on T2. And I'm not going to talk too much about this bipartiteness, but this is a very nice way of repackaging the information. So this is where quivers come in into the game. So you can actually realize these Calabi-Yau alpha and Calabi-Yau varieties both as this quiver variety and then also as sort of a moduli space in terms of the gauge theory. And this bipartite graph, you can think of this as brain tilings or descents as you wish. But we want to go beyond dimension 3. So this is the stuff that Amichai was talking about yesterday. So this one is the Calabi-Yau 3 case, where you have D3 branes perpendicular to Calabi-Yau threefolds. Now what Ami drew yesterday was sort of the T-dual version of this, where you have configurations of D5 branes and N5 branes. The details are not so important. And you can, but what if you take Calabi-Yau fourfolds, right? Because I got these reflexive polytopes in dimension n, I have the data for these. I can do Calabi-Yau 3, 4, 5 so far. I can't do much more than 5 because Calabi-Yau 5 requires delta 4, and I don't have data for delta 5. But interestingly, as far as string theory is concerned, I can stop here. I don't have to think about Calabi-Yau 6 because there are not enough dimensions in string theory to accommodate this. So I don't have to, well, you can do it. It'll give some very interesting mathematical results, but physics, not so clear. But so you can do dimensions 3, 4, 5. So these are lattice polygons, lattice polytopes, and lattice polyhedra, and then lattice 4 polytopes, and each of which will correspond to some brane configuration of such a type. It's not important. So of course, then these 16 were done, and all of the gauge theories were done for these in an early paper of Rak and Ami. And of course, we've done much more than that because of this theorem, any toric Calabi-Yau, we can construct its gauge theory. So that's kind of nice. So in particular, the 16 can be done, and there's some nice quivers, representations that happen here. Just to remark, I've talked about the tilings, the bipartite tiling of a doubly periodic plane. If you tile a genus G Riemann surface, you also get a Calabi-Yau, a quiver variety, which is Calabi-Yau 2G plus 1. But again, we're not going to talk about this bit. We're going to focus on these configurations, right? So now, very little is known about this and this. So you can see the date of this paper. So the gauge theory have just been constructed for these in January. And so in some sense, we want to use some of the physics to shed light on what can we say about the topology of Calabi-Yau, high-dimensional Calabi-Yau varieties, Calabi-Yau affine varieties, or, if you wish, compact Sasaki-Einstein manifolds. So here, so sigma spans. Sigma is a surface here. It's 4 to 7. So complex dimension, so real dimension 4. And it's the wrapping.
What is it? What is it? I mean, if you don't
Yeah.
want to
So
say it,
if you, so the sigma is actually the Newton polynomial. The defining equation for sigma is the Newton polynomial for the toric variety. Yeah, that's a. Yeah, so, and then you can sort of think of the brain as sort of wrapping part of that. But the nice story is that we know exactly what the sigma are. I mean, the defining for these. So here it will be, because the polytope is 3-dimensional. You would need a 3-variable thing that's been defined by its polynomial will be ZW, say, and another variable U will be defined by 3 complex variables. We can, yeah.
sorry, keep going.
So now, what is truly remarkable about the ADA-CFT correspondence for mathematicians is that statements about metrical and topological, about geometry, symplectic geometry, and about algebraic geometry can be mapped to statements in quantum field theory. I think for physicists it goes the other way around, but I think the majority of you are card-carrying mathematicians. So here's something that will interest you, because this correspondence says that there's an equivalence of theories. I should be able to map anything on this side to this side, right? So in particular, something that can be mapped is the volume of the Sasaki-Einstein manifold. So this is a result due to Martelli, Sparks, and Yau between 05 and 06. And it goes under the sort of the paradigm that a-maximization is volume minimization. Okay, now what do I mean by this statement? So, well, first of all, the volume side is clear, right? I have some Sasaki, I have some 5, in this case, some 5 manifold, some compact 5 manifold with Sasaki-Einstein, and I can compute its volume. And in fact, what these guys compute is the normalized volume, is this volume divided by the volume of the 5 sphere, which we know is some n factorial, the usual n sphere volume. So they compute this volume. And they ask themselves, well, what should this volume be in terms of the physics that lives on the brain? And it turns out a truly remarkable fact, there is a procedure called a function, a central charge function. This is a conformal field theory. That's exactly this. So I'm not going to get into the details of a-maximization, but essentially it says that because it's a super conformal field theory, there are these things called R charges, and there's a central charge that interligator and Weck tells us. You can write it in this way in terms of these R charges. And then in the specific case for X3, Calabi-Yau affine threefolds, you can expand this thing out. Well, here's the determinant. And then A is the area of the toric diagram, and you have this function. The point is, once you have this function, its relationship with the volume on the other side is very precise. It's exactly equal to this. And this is due to early days of ADA-CFT. Right? So, in other words, now here's something quite remarkable, right? A priori, these things, they come from completely 2 different worlds. Well, on one side, I'm computing volumes of Sasaki-Einstein manifolds. On the other side, I'm computing a central charge function in a conformal field theory. Right? But because of the remarkable correspondence that's known as ADA-CFT, this reciprocal relationship is true. Right? So, I mean, of course, you can normalize this, right? So, in particular, this gave them a very nice result for Martelli, Sparks, and Yau, is that because I'm just taking, okay, so maximizing one with respect to this R charges is the minimization of the other one with respect to the root vector. So this volume depends on the root vector. And in particular, because this is some cubic function, and I'm just doing minimization of this, this implies that the normalized volume of all Sasaki-Einstein 5 manifolds are algebraic numbers. So that's a very beautiful corollary of this fact. And so how do you compute this volume? So it goes both ways. If it's easier for you to compute volumes, you do the volume. If it's easier for you to compute the A function, you do the A function side. So whichever side will facilitate the other. When they were doing this, they found that it was actually easier to compute this volume in a very beautiful way that allowed them to compute the central charge function in the conformal field theory. So this story, unfortunately, is not so clear for Calabi-Yau manifolds greater than, for dimension greater than 3, because the conformal field theory in there become much more intricate than conformal field theory in 4 dimensions. So let's just run an example of this kind of computation. The first thing you do is you take one of these and you resolve it completely. So you resolve this by triangulation. Right? And then this is a bit faint, but so physicists call this the altonormals the PQ web for other reasons. But then you take one of these, you just sort of found the dual diagram to this. And then you compute the Hilbert series for this toric variety with these particular gradient, right? And then their formula tells us that this Hilbert series with a fully graded multivariate, so it's a multi-proj Hilbert series. It's just computed by this very beautiful combinatorial formula where U, I, J are the outward normals to this. Okay, and then step 3, you take the Futaki-Tian-Yazaldich expansion, which is if you get one of these things, you take the limit in this way, substitute this. So this is of course very much related to the so-called Futaki invariant. You do this expansion. So this looks a bit obscure. So what you're doing in this is you take this, so Hilbert series is a rational function. So this is some rational function. You can do partial fraction expansion, and you extract the leading order, right? The coefficient of the leading pole is exactly this minimized volume. And that's a very beautiful computation. And then so it's this volume, and then what you do is you take this volume and minimize with respect to the Reed vector, especially at the last component set to n, because that's our convention. So now just to remark, we've done something here that requires the resolution of these toric varieties. Right? So usually what one does in these resolutions is called a fine regular stellar triangulation of the polytope. So fine meaning that all lattice points are involved. Regular meaning all of these are determinant plus minus 1. This is stronger than usual definition, but we need this for smoothness. Stellar meaning that the apex is a star triangulation from the center, which is we always have because it's a single interior point at the origin, and then and it's a triangulation. So here's the one that's the delta 2, the dual delta 2 example. So this is an example of a first, and this one, if you can see, there's a single origin here, and you can check that all of these determinants are plus minus 1, and so on, and all of these are. It's a regular triangulation. There's a theorem of Batirev and Benjamin Neal that for n equal to less than equal to 3, all of these admit a coherent equivalent resolution. So this is possible. So that's great. So for delta 2, we actually we can get 16 smooth Fano varieties in dimension 2 and 3. But for delta 4, it is no longer guaranteed, but let's just consider the ones that do admit it. So now what do we do? Well, now I get this smooth variety, this smooth compact toric variety, right? So the strategy is then, can I say something about the Sasaki-Einstein volume using and their relations to topological quantities of this smooth complex variety? So that's well, I mean, because in dimension n equal to 3, a lot has been done. Higher dimensions, we don't know. Right. So I did lie. There is higher in my talk. Okay, so for example, we can compute. I mean, this is standard, right? You can compute Betti numbers, Chern numbers, and whatnot when you have a smooth toric variety, smooth compact toric variety. So for example, in dimension 2, the two Chern numbers is this integral, and of course the top one is just the Euler number. And you can check that this is actually equal to, for any one of these things, is actually equal to the number of perimeter points for the Euler number. This is standard. But what's less standard is that we checked that the number of this Chern class is the number of the perimeter points of the dual, the polar dual polytope. And in dimension, you can do, then you go to the next dimension. So these are the Chern numbers for the Fano threefolds. The top one, again, is the Euler number. And it turns out this is 2p minus 4, where p is the number of boundary points on this. And the middle one is just 1/24th of the Todd, the third Todd class integrated. And the first one is this. But it just turns out by brute computation, you have also this mirror symmetry. And the middle one is fixed at 1. It would be very nice to explain this, but we ran out of steam. And it might be obvious. If this is obvious to anyone, please let me know. That the Chern numbers of reflexive of the smoothings of toric varieties for these ones have this very strange mirror symmetry. This is not Calabi-Yau, right? So it's kind of interesting. So now let's do experiment, right, which is always good. So let's compare the minimized volume against these various Chern numbers. Just something you want to do. So let's just draw for the 16, for example. You plot the lower bound. You plot the minimized volume versus the Euler characteristic of the resolved, the smoothed toric variety. So if you plot it, well, you say, well, it's really nice. We have a lower bound, and you can then if you check what these lower bounds are, you see they're indeed the 5 smooth Fano. I mean, sorry, they're the 5, sorry, not the 5 smooth Fanos, they're the 5 abelian quotients of C3. The 5 smooth Fanos are somewhere else. This is nice. And then if you plot this combination versus this, you find there's also a top one for this product. And then again, you go and check which one that is. It turns out to be the the cubic surface. What we call dp6. And the upper bound is at this number. Remember, all of these things are algebraic numbers. So that's kind of nice. So here's a sample calculation. So we've got to zoom in onto abelian obifolds somehow of Cn. But it's very nice. I mean, this is the kind of problem you can give to an undergraduate. You strip away, at this point, you give this problem to an undergraduate. So in delta 2, for example, C3 modulo Z2. This is the total space of the anticanonical bundle over P2, P3, and P4. And you run through the Martelli-Spark-Yau prescription of computing the Hilbert series. You get this stuff. It gets a bit messy, right? And so, remember, these are the vertices of this polytope. Note that all of these vertices are co-hyperplanar because of the Calabi-Yau condition. So I can set the last one to say, for example, 1. Right? That's some stuff. And I can, after this, I can do a fine regular stellar triangulation. This is the incidence data for this, and I can get this huge stuff. It's something. And then you do the Futaki Tian Yau Zeldich expansion for this. I mean, what you do is you set all of the different t's to e to the mu times some parameter, and then take the limit. Or in other words, set all of the t's to be equal, and then do partial fraction expansion, extract the top pole. Right? And you get some stuff. Right? For example, you get these. Right? After you're done. And you can see explicitly the appearance of the components of the Reed vector. And now what you do is you take one of these things and you minimize it using first-year calculus. And I get a third, a fourth, and a fifth. This is certainly the hardest computation I've ever done to get 3, 4, 5, because I know the answer is 3, 4, 5. Why? Because I know the normalized volume of this. The normalized volume of C3 is the real cone over S5, and it's quotiented by Z3, so I'm going to get a third of that volume. But this is great because, after all this, it's okay, it's not that bad, but it's, in Mathematica it still runs about a minute or so, and you get the correct answers. It's a fantastic problem for large clusters, large parallel clusters of undergraduate students. So that was the 16, right? So we did this for the, so we did for the 16. So now you can do the 4,319, which would take about a week on Sage. It's okay, a week is doable. So after a week, you find this plot of the Euler number versus the minimized volume. And again, this beautiful thing. And you track what these are. And these are indeed also the orbifolds, the abelian quotients of C3. Now, of course, we know that we can compute these, so these are just 1 over n. What is not obvious is that why the abelian quotients should be the lower bound of this curve. And then you can track again what the upper bound is.
You mean this is the polytopes that are triangles? What's that? Or
yeah, that's right. That's right. For these ones, they're simplices. yeah. The upper bound, in this case, there are 2 of them, and they're these ones, if you really care. But what is interesting, again, all of the slices in every direction is a Del-Petzel 3, so it's a cubic surface. So it's a multiply Del-Petzel 5 direction somehow. And why? Maybe it's because it's very symmetric. Don't know. But and again, you can compute them. So these ones are nice because they're rational. But generic points here are huge algebraic numbers, roots of God knows what. So then you can just go take the data. Now, if 4,000 takes about a week to run on Sage, 473 million is not going to finish in our lifetime. So we had a choice. We can wait, or we can take a random sample. So we chose the latter because our lifetimes were finite. We took about a 10 to the 4th number of samples, let it run for 2 weeks out of this for every number of respective vertices. And the lower bound, so there are 1,561 of 4 polytopes in this data set. We checked this, and it's all fine. So okay. So this proposition is true. You can just show this by just volume techniques. So what we conjecture then is that any Gorenstein Fano delta n-1 has this lower bound. In particular, this lower bound is saturated by abelian quotients of Cn. And it is probably true that for any toric variety, this is also true, because these are sort of one single points. All of the other toric varieties will have toric diagrams bigger, and the bigger you go, the smaller the v gets. Whichever direction that makes this work. So, but this needs to go. So we think that this is true for arbitrary toric variety. Yeah, so I won't go into the remark about algebraicity here. Well, that was just one topological invariant. I gave you a list of these, right? So in dimension 2, there's not much more to do, but it's just this dual point. But in dimension 3, I have this relation. I got 2 non-trivial Chern numbers. And combinatorially, I have 2 sets of integers, namely the number of boundary points times 2 minus 4, or the number of boundary points of the polar dual times 2 minus 4. So, and then you try to plot that one, and that's kind of nice. You see, there's an upper bound. Okay, so for this is good. For the 4,300 or so, we had to numerically compute this because the minimization, because the algebraic numbers got so huge, we had to numerically do it. So numerically compute these and do a best of fit. And if you compute the line, then you give it some big number. And if you find the slope of the line, it looks like it's 3 to the minus 3, and for this one, it's 4 to the minus 4, which is really cute. I have no idea why, by the way. Just this is experimental physics. So the conjecture then is for any reflexive polytope, there are 2 bounds. The minimized volume of the Sasaki-Einstein manifold, the normalized minimized volume, sits in between 1 over the Euler characteristic of the resolution of the toric variety, and the upper bound is by some linear relation, we think, n to the minus n for dimension times the top power of the first Chern class instead of the top Chern class, which is the Euler number. So this is a very nice duality relation, which is really cute. So, but this is purely conjectural. Now, in physics, if you have 2 data points, that's enough. It's a theorem. All right, and we wait. But of course, Professor Yau is a card-carrying mathematician. We'll have to write conjecture in. Actually, I probably should. If he sees me write conjecture without quotes, he may get upset. So this conjecture has quotes. But it's very suggestive, right? When we're talking about thousands, tens of thousands of data points. But of course, in number theory, this is nothing. But in geometry, this is much more convincing. So, of course, that leaves us a lot to do. So first of all, I want to understand the mirror symmetry of the Chern numbers. This is kind of strange. I mean, probably use some version of reciprocal Riemann-Roch. I mean, there should be some index theorem that says. But I try to compute these Chern classes analytically and then try to see this relation of the top. It's kind of cute, right? You just take one of these things and you take its polar dual, right? And you compute all Chern numbers of one of them, and you take all Chern numbers of the other, and they're completely flipped. So I'm sure the argument will be very clean when a card-carrying algebraic geometer shows me. And then there's this lower bound, which is probably true for all toric Calabi-Yaus. And there's the upper bound, which should be, possibly at all del Pezzo 3 or cubic surface vibrations. And now that's from the mathematics side. And ultimately, we want to use, so in physics, bounds on these central charge functions are very, very important. Right? So we know very little for any serious bound statements beyond the one in dimension 4. So can we use this Sasaki-Einstein volume to make any statements about bounds on these? But that's also to be done. And of course, non-toric is still further work. So I think I'll stop here. Thank you. My collaborator is asking my how talk went. I don't know. Ask me questions first.
Do you have any question or comment? Yeah.
So, one comment is that because all the varieties you showed us are essentially schemes over the integers, they can be reduced modulo some prime. And therefore, you can count rational points over fields of positive characteristics. And so, I think at least some of the statements about Chern classes and figure out on about your fourth last could be looked at that way, because that has implications for the Hodge structure of the cohomology.
That's interesting, thank you. So there's actually, that's a good point, because there's a recent program that Philip Candelas has been working on, is to count rational points in Calabi-Yau. And I tried, so his program is to relate that to the period integrals. So he has some very nice results there. But that's a nice suggestion. Maybe I should try to use, gosh, I have to work not over C. I'm used to working over C, but yeah, that's good. Thanks.
Do you have any other question or comment?
Yeah, just to clarify one thing, I mean, the Fanos, you had these Fanos X, which were often singular.
Yeah.
And then these Sasaki-Einstein manifolds, which were always smooth, or?
I believe the Sasaki-Einstein is always smooth. Yeah. But I mean, we do the one that we smooth out by hand is the actual Fano variety. But that's not, apparently that's not always doable for high dimension. But for dimension 2 and 3, they're always doable. You can completely smooth one of these. But I believe the Sasaki-Einstein ones are always smooth. And you can compute a nice volume for these, which are algebraic numbers, which is kind of nice.
Do you have any other question or comment?
Thank you. Well, since I'm the last speaker, I'd like to take this opportunity to thank the organizers. So I think we have to very much. It's been a very nice conference.